Hi, I'm Patrick, one of the co-founders of Kessler Labs. What I want to show today isn't a polished product demo, but really exists to showcase the workflow that the Arcturus platform enables. Specifically, we want to showcase how Arcturus lets teams develop, test, and build certification evidence in parallel, instead of treating certification as a painful late-stage process. To demonstrate this, I'll be building a simple attitude control system for a small satellite. Looking in the code here, we can see we start off by importing three components: a PID controller, an IMU, or inertial measurement unit, and a reaction wheel. These come from the Arcturus core library and represent the sorts of components that might appear in many different flight software stacks. The important thing is, if we kind of jump into one of them, that these come pre-certified. In isolation, each one already meets DO 178C Design Assurance Level A requirements, including full structural coverage. This means that we're not re-implementing low-level logic and don't have to reprove it from scratch each time. We also get full control over the parameters that matter for the mission, like in the case of our PID, our gains are exposed. These are quantities which we tune to match our specific system, or in the case of our actuators, we might introduce some limits or physical properties. Now, down the bottom, we can see the testing panel. What's important is that all the tests we'll be running are requirement-driven and not handwritten one-off tests. For this demo, Arcturus has automatically generated certification-relevant scenarios and linked them directly to the applicable requirements. Today, we'll mostly focus on nominal operation. This test sees us proving stable convergence under nominal conditions with all of our sensors healthy and actuators at full authority. We can see here some of our requirements were automatically linked to this testing scenario as well. We'll also be having a look at scenario 4, our timing and scheduling stress. Here, we look to prove that our real-time deadlines are met under the worst-case compute load, and that our worst-case execution time budget is suitable. In traditional workflows, this sort of structure would typically appear months later, pretty far down the line. Here, it exists immediately and is a priority from day one, helping to shape the development process. Alongside testing, we also track coverage in real time. This includes functional coverage, are requirements being met, scenario coverage, have certification test cases been exercised, and decision coverage, have all of our logical branches been explicitly handled. This matters because in certification, unknown logic paths are showstoppers. Arcturus surfaces those gaps as we write code and not during an audit, allowing for very rapid amending of these gaps. Next, we can have a look at our certification documentation. Here is the software design document. I'll go ahead and expand it quickly. We can see we've kind of provided an outline for the system as designed so far. For example, we can see our controller's equations, parameter definitions, and also see the currently active gain values. Critically, these values will always be consistent with the source code, which we'll see shortly. This sounds like a small thing, but in real programs, documentation drift leads to a ton of rework and delay. Jumping back into the system, we'll go ahead and run a quick simulation. We've got a little 3D visualization of our satellite here, as well as a graph mapping its movement. These are demo-specific provisions and likely wouldn't exist in the final product. But if we go ahead and run our simulation, our goal today is to make the satellite rotate exactly 90 degrees and hold that position. We can see we successfully rotate 90 degrees and then proceed to overshoot. We then aim to correct and then kind of do this little dance about the 90-degree point, slowly converging toward it, but certainly taking way too much time. If we jump into our testing tab, we can see We failed on our first test, which is to converge within 60 seconds. We also fail on the worst case overshoot. Here, for an 180-degree rotation, we actually end up overshooting by 180 degrees. Our requirement is that across the full range of motion, we only ever overshoot by less than 5 degrees, so we've obviously failed on this front too. To amend this, we'll jump into the code and update these PID parameters. As mentioned, these are system-specific values that allow us to tune our control system to really match the system under development. So with these changes in mind, we can see a few things happen. Firstly, if we jump into our software design document, scroll down a little bit, we can see our parameter values have been updated to match. As we make changes to our code, our coverage is also reassessed. In this case here, our decision coverage hasn't changed, and our functional coverage shot up after running our first test, because we did indeed pass 1 of 5 tests. In a traditional team, this sort of tweak late in development would trigger massive document rewrites, test redevelopment, and potentially weeks of recertification churn. Here, it's just a part of normal iteration. Now, after tuning, we can go ahead and run our tests again. And we see a nice clean convergence, well within that 60-second window, and in this case here, little to no overshoot, and in the worst case, only overshooting by 1.4 degrees. If we jump back into our testing panel, we see that we indeed converged within the time, we've verified our overshoot across the full range of motion, and this case here has passed in software mode, saying that we've met all of our real-time execution deadlines. However, the bottom 2 test cases down here have been skipped, and we can see we are yet to pass our nominal operation test case. This is because we have to implement control mode logic. If we dive into our requirements over here, we see we specify a couple of different modes that we want our system to kind of transition into. In the code, we can see we specified them here. We specified kind of the limits that decide whether or not we jump into those modes. And we've written a little function that allows us to decide which mode we should be operating in. If I jump down here, we can see I've commented out the section where we actually apply this code. Now, if I jump back into the coverage tab and go ahead and uncomment that, you can see our decision coverage drops. This is because we're now using this interpret IMU function, which returns one of 3 control modes, but we're never actually explicitly handling those modes. We return one of 3 values, but which value we return doesn't actually matter. This is not okay, and it's important that we explicitly handle each of these modes. So I'll go ahead and uncomment this section here, which allows our decision coverage to jump back up. Now, what this does is allow us to handle each of our control modes and really update our underlying control logic. So for our course pointing mode, we might expect a faster correction. For aggressive stabilization, a rapid arrest. And then in fine pointing mode, we'll perform kind of the normal operations as we were doing before. And then down the bottom here, as normal, we're kind of commanding the wheel. So with these changes in mind, we'll go ahead and run another simulation. And we can see our functional coverage jumps up to 100% and our scenario coverage jumps up. This is because we have now passed all 5 of the requirements-based tests we specified and passed on the nominal operation test scenario. This really enforces the certification as you build aspect of the platform, instead of relying on an after-the-fact review. Now, the last step we're going to look at today involves test scenario 4, which sees us simulating our software on hardware. Because the Arcturus platform controls this hardware interface, we're able to actually simulate on that hardware. So if we jump over to hardware in the loop simulation mode, we can see we're now testing scenario 4. We go ahead and run it and see we get a little warning here. And jumping back up to our tests, we see we're now failing on test 3. This is saying that we missed our real-time deadlines nearly 6,000 times throughout execution. Now, this can be due to a number of reasons. In this case, because our integral gain on our PID is incredibly small, is not something we even consider in our control mode logic, and contributes to the computational complexity of our program, I'm going to go ahead and set this to 0. What this will do is, as the code compiles, it'll get rid of this term in the PID calculations, saving us a bit of time. If I go ahead and run the sim again, we can see now we're passing across all these test cases. And for this use case, where we've only got one requirement linked, we can see we're now passing test scenario 4. This change kind of improved our timing, helps us pass real-time constraints, again updated all of our documentation, and has preserved our coverage, actually improving our scenario coverage. Again, this did not include any separate certification sprint and happened alongside development, and was actually prompted by the hardware simulation we're accommodating. So today, we've implemented this PID controller from scratch, didn't have to hand author our tests, didn't manually update our documentation, and didn't have to wait until the end to worry about certification. As the system evolved, our requirements stayed live, coverage was completely visible, documentation remained consistent, and our hardware constraints were tested and enforced early. This is the unlock Arcturus delivers. Certification moves with development, not against it. Thanks for your time.